Hey guys, welcome to Experiments and Data. Now, one of the fundamental things we like to do in the scientific community is investigate something that we really don't necessarily know what's going on, don't understand the law, or maybe beyond a simple formulation of how we expect the world to behave. One of those formulations might be the opinions of humans. We're not sure exactly how we draw those opinions, what influences them, and what law would govern them. And so what we do is we gather data in an experiment, and the fundamental idea is we want to see what might be influencing things, what might be an explanatory variable. And so in general, we try to, in an experiment, it's just not an observation. We try to influence something and to see if that influence can be measured. Because of this, we need to be very careful. We want to conclude that we understand what might be influencing and to what degree something's influencing. But in order to understand that, we also have to have a baseline of what uninfluenced behavior is like. So the first thing that we're going to do with an experiment is we want to understand that it is absolutely necessary to have what is called a control group. A control group is going to be a basic set of individuals, whether it's humans or balls or whatever you're measuring and how you're measuring it, that is going to be uninfluenced. It somehow exists in the natural state. So, uninfluenced, some natural state. So, for example, maybe you think the color orange will help people in a restaurant spend more money. Well, then you need to have a natural state where the orange isn't present, and you observe how they behave, and then you at the same time have a second place where orange is introduced alongside of the group that does not have the orange. Now, in general, the control group needs to be done simultaneously. And the reason for this is that there are external conditions that can affect how people are behaving. So it's very possible that something that happened earlier, and when you repeat it later, that some other variable is messing with you and that you're unaware of it. So when we do control groups, we universally expect them to be run simultaneously as the experimental group. And these are the ones that are going to be influenced, and they're not in the natural state. So if we run these simultaneously, then there are conditions that are better controlled, that time can't affect things, and other possible exterior variables. Now, when we design an experiment, it's very important that we use this concept of randomness. So there should be a very simple random procedure that splits the control group and the experimental group. We want no human to make a choice of, oh, they should be in the control group, they should be in the experimental group, simply because we don't want that possibility of bias. Random removes that bias. Now, we generally call the thing that's going to be an influence a treatment. Now, that doesn't necessarily have to be the word that you're like treatment for medical, but it is a standard term. So, for example, maybe you want to study how different forms of pedagogy and teaching would affect how you learn. Right now, you're getting tons of information online. Are you going to get better grades or worse grades? Are you going to be more stressed or less stressed? Is it possible, quote, that the online situation, viewed as a treatment, is causing certain things to occur, while if you had been in an in-class setting, it wouldn't have. And so we would have a control group that would be in the in-class setting, simultaneously as a control group that would be in the online setting, and then we would watch things and check what's happening and measure things. But if the treatment is solely to be in an online setting, then you need to try to do everything else alike. We want the treatment in the experimental group to be a single factor change. So if I was to have a in-class group, an experimental group, I would need to follow exactly the same lecture schedule, exactly the same lectures, exactly the same homework, exactly the same exam, exactly the same dates in moving, so that homecoming couldn't affect one or the other, or Thanksgiving would interpose one versus the other. The only difference I would want is a single factor change. In addition, I would not want one teacher teaching the control group and a different teacher teaching the experimental group. It could be as simple as videos are recorded on a PowerPoint and presented in TV with the professor present, and then answer questions. And the other one be the same videos presented and answer questions via Zoom. In other words, try the absolute minimal amount of change so you can measure what the onlineness or non-in-person portion would be. When you have an experimental group that doesn't have a control group, that is the biggest red flag. Now let's make a red flag. If you're missing a control group, this is a major red flag, and you go, oh no, I probably don't want to trust this data. However, sometimes data does come to you not in a control group, and then there are a zillion questions that need to be asked as to what is occurring. Now, bias, not the mental form of bias where you're biased against someone. Bias mathematically is when the data is shifted and moved in one direction or another, needs to be clearly addressed when we're doing this. And one of the first ways to address it is we don't necessarily want individuals to know that you're in one group versus another. You don't necessarily want to know them they're being tested, but ethically people should know they're being tested. So for example, we could advertise a class that's going to be in class and online and tell the students we'd like to assign you randomly to see how the performance is measured. And everybody knows they're inside of an experiment, but they don't necessarily know all the particular aspect of what is going to be tested. There's a little blinding done to the people. Now what's typically done with this word blinding is when we do a medical experiment, I want to give you a treatment. Some people, when they're being treated, just because they're knowing they're being treated, actually their body reacts and their mind reacts and they feel better. And so, if we were having a group of people and we want to test whether one treatment was helping them, but we have no other treatment to give the control group, we'll actually give what's called a placebo, a pill that is a sugar pill. We will give each group a pill as if they're in an experimental group. So the control group and the experimental group do not know who is whom. Now, obviously, if you're in a drug trial where you might die because your disease is terrible, you might not be happy to find yourself in the control group. But as a medical researcher and a statistician, I need that control group. I need to see how things are proceeding. However, let's take, for example, pancreatic cancer, liver disease. We've got tons of data of how it proceeds and where it goes. So where people's lives are at stake, we might have enough information that we're happy with prior existing control data, and we have solely an experimental group. Usually that is done in very extreme situations. We very seldom do it. It's usually done in situations where we may have somebody that basically has a 1% chance of living. There's really little hope in it, and so we choose to put them all in the experimental group. Right now we have a vaccine, 3 of them under research, and they have control groups in those. Even though we have a worldwide pandemic, they created control groups to make sure that we can compare the experimental group and the control group. So some people are receiving vaccines that aren't vaccines. They're sailing water, but they're participating to make the world better. Now, There's a second form of blinding that is done. And that blinding is done to the researcher. Let's suppose you've developed a treatment that you think would just be an excellent treatment for people that are trying to cure themselves of, let's say, a drug addiction or an alcohol addiction. And you think you can save tons of people. And on top of that, maybe you'll make some money. So if you are involved in this research, you have the potential for financial gain, the potential for honors, a Nobel Prize, who knows? So we don't want you, the researcher, to have the potential to inadvertently skew the data when recording or asking questions, how they feel, what they're thinking, the pain scale. Why? Because you might push the data in the wrong direction. So with this control group and with the experimental group, which have been randomly placed here, and they are blinded to who's doing what, it's useful for you to have an assistant, a machine, that assigns the people into these groups, produces the bottles of placebos and the bottles of the treatment, and then when you're involved in the research, you actually yourself know no difference between which is in the control group and which is in the experimental group until you start unsealing certain materials after the research is completed to find out who was in which group. So the patient or the participants get blinded, but the researcher gets blinded. This is fundamentally important. We call this double blinding, or a double blind experiment. This is truly important, and one good question I can ask about double blinding is, why do we do it? And the answer is simply to reduce or eliminate bias. It is used to make sure that the results aren't pushed in one direction or another. Now, we gather data and we like to know, well, is this good? So let's look at like a pain scale, and we have our control group is, let's say, normally distributed around a 6.3, where pain is measured from, let's say, 0 to 10, 10 being bad. And then we have a treatment group that might be normally distributed around 6.2. Now, one would perhaps not be sure that it wasn't just an oddball occurrence that the treatment group was slightly lower. It doesn't look like it's very effective. Maybe it's possible that the 6.2 was affected by the treatment, and that's why it's lower. But maybe 3 or 4 people simply were reacting to a placebo effect even though they were in the treatment group and said, yeah, I'm feeling better, less pain. So we would like the results of things to be what we call statistically significant. And the idea of statistical significance is that there should be some way to measure that this effect that we're seeing is not just a random effect. And pretty much our standard is that if this is happening randomly because of a few people behaving differently or a few people are actually getting better, we would like the statistical significance to say that less than 5% of the time would this change have occurred randomly. We want to be 95% sure that it is our treatment that is effecting this change. And so we want to develop a method by which we can make sure that we can measure statistical significance. Now, I've already mentioned this thing called the placebo effect. The placebo effect is simply people that believe that because they're receiving a treatment, they're getting better, my headache is relieved, my pain is less, my mood is better. And that placebo effect has been well proved, that we can actually demonstrate that when people get given sugar pills, it can relieve their headaches. We can give them starch pills and it relieve their headaches. We can give them salt, that's a bad idea, a low sodium pill, and it will relieve their headache. In other words, some people react bodily and mentally to a placebo. And one of the reasons that we blind the patients is to eliminate placebo effect. And the reason that we blind the researcher is to eliminate his conception of bias towards their desire. We know the placebo effect is real because we did a test on placebo effects to see how well people that were being given placebo drugs reacted to certain situations, and they were deemed to be statistically significant. Therefore, because of our experience on previous experimental, we know we fight against it. So someone did these experiments with the placebo effect to determine it is real, it occurs, and therefore the double blinding is necessary to protect against that bias. Now, the process by which we create an experiment needs to take into account the double blinding so that the process can be done. It needs to be designed so that randomness is used as much as is possible, that the single factor that's going to be changed is clearly looked at, and populations of the whole group have to be well defined so that when we're done we get some statistics that have some valid meaning. This is hard to do. So design, implementation, and analysis in its totality is hard. We have entire courses designed around teaching students how to design and implement things so that that is done well, and then an entire course itself around analysis. So this is not a trivial process by which we work at doing this. Take, for example, the design stage of where we want to pick people to treat with a drug. What happens if this drug has a tendency to help one gender more than another? For example, it works well for women but not well for men. But we are unaware of that, and our design didn't take a gender into account in making sure our population was well represented. Or there may be genetic backgrounds that have to be looked at very, very carefully because some of the drugs actually affect certain genetic backgrounds different than another, and therefore the treatment effect cannot be seen because that population is actually truly prohibited from using that type of drug. There are many things that could come into effect that can mess with you, and you can't begin to know them all. So when we do a design and implementation and analysis, we have to write up every single little step, every little thought, everything that's involved in this to make sure that what we get is something of very clearly defined information so other people can look at it and, most importantly, repeat it. Now, in order to gather statistics, we have to realize that we have a fundamental population, and from that population we make a sample, and from that sample we get things like X bar, the average of something, we get a standard deviation, and we would like to infer something about the mu, the average in the population, and the standard deviation in the population. This process of drawing that inference. Now, it's a little bit dangerous to draw these inferences if you have too small of a sample size. So obviously, right off the bat, our simple random sample, there's a sample size n, and this is going to affect it. The next thing is, depending on your value of n, that n obviously affects your calculation of x bar, calculation of s, and it's going to affect how you're going to conclude here. So it looks like it can be a fairly complicated procedure by which we need to understand statistics. So we're going to do one of these procedures, and we're going to make it as simple as possible so that this procedure can show how these factors get impacted in any study. So we're going to measure something that has a clear yes or no result. Better? Yes. Like the candidate? Yes. Like the law? No. We're going to try to get it down to the most simple yes or no answer so that we can see better or not better. Agree, doesn't agree. Votes for, votes against. That's what we're going to look at. That's a pretty simple type of chart as well, because let's look at, say, yeses and nos. So we're looking at whether a population is going to support a measure. Or how about just yeses and other? Because if they don't vote or they're not sure, let's just count the definite yeses. So if we look at a situation where we have a characteristic, and let's call it characteristic A, we automatically make the other group not characteristic A. And so there's just either you're with us or you're against us. You're part of the solution, not part of the solution. We're going to do that. And then we're going to measure what percent are here. So for example, if we're talking about who's going to vote in a candidate, if we're convinced that this candidate is going to receive 56% of the vote, we want to say we think that candidate's going to win. We're predicting the future. Or we think the measure will pass. Or we think that the drug seems to make people feel better. So we're looking at one characteristic. And so the first thing we need to do is, when we have our sample, we have to then know how many say one and say the other. And we immediately calculate the number that like characteristic A over N is what we're going to call P hat. The hat indicates, like the Y hat in regression, that it's an estimate of the real population. So let's do a simple example of this. Let's look at the upcoming hemp. I'm not going to do the medical one. The hemp law, where are we going to make it legal for farmers to grow and raise hemp in South Dakota and use this for making fabric, CBD, oil, everything that's not associated with the drug but associated with the plant itself. And let's say we go out and ask 400 people, and I don't want to call it, and we're going to ask 400 people. The answered were 380, and then next comes the important fact that the characteristic A, we're going to say, is likes / supports, and let's say that number was 201. Now, what are we going to do with this information? Well, first off, we should observe that not everyone answered. So we have something called the response rate. Now, the response rate in this case is 380 out of 400. And let's get that value. Why, that's 90%. So 90%, over 90%, sorry, approximately 95%. 95% of the people said, yeah, we really like this question, we're going to answer it. And 5% said, bug off. With a response rate at 95%, we're very happy to proceed. In other words, if this group that were asked were truly asked in somehow a simple random sample, we feel that that sample wasn't biased by our choice. We didn't set up the sample as a convenient sample in the dorms. We didn't set up the sample by just going to the mall and asking people at the mall. We somehow randomly reached out in the population and got 400 people asked and 380 answered. That in itself is hard. This response rate makes us happy. In general, a response rate of around 90% or 0.9, very strong. A response rate of about 0.8, strong. A response rate of about 0.7 something, weakly strong. Just like we did with the correlation coefficient, we like these numbers. If we have a response rate of around 60%, very weak. We probably should not be doing further investigation as a mathematician. So we have a response rate of 95%. So we feel that if the simple random sample was created well, then the answers we have collected have not converted it to voluntary, which is a bad sample. So now we're convinced we have a good sample. Well, we now throw away the 400 and we have answered is 380. The yeses were 201. We're ready to calculate our p-hat. The number of our characteristic, 201, divided by our 380. Now I've got to pop up a program here to tell me some values. And what we get is 52.89, or 53%. We have these numbers, and we can say 52.9 if you like, but we have a number. The rounding at the moment I'm not too interested in, because we have to come up with what we call our degree of accuracy. So we see that from our sample, 53% of the population looks like they support this measure of creating hemp industry. Now, is that large enough beyond 50 for us to say, I'm confident? Am I confident this hemp law will pass? And so how do I convince myself that that's a good enough statistic, this 53? Well, first off, I know this number is going to be wrong. When 100,000 people vote, it's not going to look like this. It's not going to be exactly 53%. In other words, I'm kind of hesitant to conclude that the real population is 53. What am I willing to conclude? Well, first off, we have to understand that regardless of the distributions of yes or no's in the real population, that as you ask groups of people, it is hard for that data to spread out randomly in the wrong direction. But we do expect to be wrong. We expect that the real answer is in a range. So as an example, I could ask everybody their age, and they tell me their age, and then I could ask one of you in the class to guess the class average. Now, if you said 19.8, how accurate are you going to be? Maybe the answer was 20.1. Is that an accurate response or not? Now, if you, instead of having responded that I think the class average is 19.8, what happens if you said I think the class average is 19 to 21? There's a range of answers. I bet you're very comfortable with that answer because there's very few 18-year-olds and very few 22-year-olds compared to the total of 19, 20, and 21. So if you gave a range of 19 to 21, odds are the average of the class is going to land in there. But it could, average might be a bunch of 18-year-olds and we're 18.7. Maybe we got a bunch of super seniors and we're 21.8. But giving an interval as a response is far better than anything you can possibly imagine, because it allows you to be slightly wrong but still have accuracy, and because of what is called the sampling distribution. So now I'm going to draw a very important question. Picture. When you sample data and record averages from groups. In other words, let's say I sample 3 people in the group and say, what's your age, and record the average. Sample 3 other people in the group, what's your age, record the average. Repeat this over and over again. The interesting thing that happens is the distribution curve of the sample always starts looking like a normal curve. And the average of the normal curve is extremely close to the real population's average. In fact, they lie near each other. And last but not least, it turns out that this x bar plus or minus 1 standard deviation, x bar plus or minus 2 standard deviations, our 68%, our 95% comes into play. And it comes into play in the following way. When we take our population and we calculate our sample standard deviation, and we go up 1 and down 1, we can say, I expect to be correct. How often? 68% of the time. Now, that's an interval. That's an interval from x minus x up to x plus x. And that's an interval of how often you actually expect the real average to land in here someplace. But you like to be right 68% of the time? That seems like almost simply an unfavorable coin. It goes one way more often than another. Well, if you write down x bar plus 2 standard deviations, now you have an interval where you expect to be right 95% of the time. This is kind of cool. It says, I now know how to create an interval that predicts a population average in a range, and I can say 95% of the time this range is where the answer is going to be. If you like that range, if that range says something interesting, well, then you can draw a strong conclusion. So let's take this hemp example I just did, where we first asked 400, answered 380, the yeses were 201, p hat was 53.89%, and I'll use all 4 decimal nows for this calculation. What I need to introduce is I need to introduce a formula for the standard deviation of a yes-no question. And we have a formula for that. The variability of the yes-no answers is a well-known formula. So the S for asking a yes-no question, or a yes and everyone else, is the square root of the P times 1 minus P over N, which was the answered, not the asked. But we don't have P. We have a guess at it. Well, this is approximately, we're going to use that guess. We will use P hat times 1 minus P hat over N. This will be the standard deviation of our calculation. So I'm going to put this into a calculator in this case. So I have 0.5389. I'm going to multiply it times 1 minus that, which is 0.4611, divided by, in our N that answered was 380. And I'm going to get this value. So here we go. 1 second. And I get, for this number, 0.02557. Now, as I said before, I am going to build an interval around my x bar, since it's a percentage of people saying yes or no, our x bar is the p hat. We believe 53.89% of the population support the law. So what we're going to do is we're going to create our 95% confidence interval. Are we confident that the population is going to pass the law? Well, I'm going to say I'm 95% sure it's going to pass the law if this interval looks correctly. So here we go. I'm going to take 0.5389 and I'm going to add 2 of my standard deviations to it. And I'm going to take 0.5389 and I'm going to subtract 2 of my standard deviations. And this is going to give me an interval from a low number to a high number. So now I'm going to calculate those two numbers on my calculator. So the first one I get, this calculation is 0.5900. Okay, I'm going to do this calculation. And I get 0.4878. And so now I'm ready to say that I believe the real percentage of people that support passing the hemp law is somewhere between 48.78% up to 59. Unfortunately, the 50% number lands in that interval, which means I don't know really where the real population average is. Just because it's mostly above 50, I can't conclude that I'm 95% confident it's going to pass. In fact, I basically can say I'm 95% confident I don't know. I don't know where the population average is. This statistic right here was not sufficiently solid enough for me to conclude we're going to pass. Why? Well, one answer is I got too few of responses. The second answer, this number wasn't high enough. The third answer is this number was too big and it let me add and subtract too large of a number. We moved up and down from p-hat too much to get a small interval. We got a big interval. The variability of chance in the right answer is called the margin of error. So right now when I calculated plus 2 times 0.02557, which gets 0.051, we approximately have a 5.1% margin of error. Up 5, down 5. And this is why the 53 dropped all the way to the 48, and the 53 went all the way up to the 69. This is the error that can happen with simple randomness in a problem. And because of that error, this sample set that I did was insufficient to draw a strong conclusion. Now, 50% is not always the cutoff. So for example, to overturn a presidential veto requires a 60% or 66%. These are called supermajorities. So sometimes your interval that you create needs to not contain a specific number so that you're either below or above it. And that way you can draw a confident conclusion. The 95% confidence interval is equal to, you get a p-hat or an x-bar, you subtract 2 standard deviations, you get a p-hat or an x-bar, and you add 2 standard deviations. And this interval is where you're 95% sure the conclusion. And the 2s is what we call your margin of error. And that margin of error does only one thing. That margin of error is predicting the odds that your sample simply shifted your average in the wrong direction. In other words, it simply says that when you sample some people, you haven't sampled all, therefore you expect to be wrong sometimes. That's all it's correcting for. You're not saying, I know this is the error of my calculation. No, it simply says I expect somewhere in here the average to fall 95% of the time. The word error is really kind of misleading here. Now, I think it's very important for you to read the vocab from chapter 7. All right? There's several very useful words in there, and they will be occurring. All right.